All right, today we're going to tackle a concept in programming that's, well, both beautiful and a little bit scary. Recursion. It's a way of thinking that once it clicks can make some really complex problems feel almost laughably simple.
So, let's start with a little thought experiment. Just imagine for a second, what if a big, messy problem actually had a smaller, identical version of itself tucked right inside? And what if that smaller problem had an even tinier one inside it?
The perfect way to picture this is with a Russian nesting doll. You've got this one big doll, right? And your goal is to get to the very last one. So what do? You just open it, and inside, surprise, it's a smaller, identical doll. So you do the exact same thing again. You open that one. You just keep repeating that one simple action until you can't anymore. That's it. That's the core idea of recursion.
So, let's put a formal definition to that idea. Recursion is just a method that solves a problem by calling itself. Yeah, it calls itself to work on a smaller piece of the very same problem. Each time it calls itself, it's like opening another nesting doll, breaking the problem down until it's so tiny it becomes super easy to solve. Okay, so for this whole thing not to just collapse into total chaos, every recursive process has to follow two golden rules. I mean it. These are the absolute non-negotiables of making recursion work.
Let's go back to our dolls. The first rule is what we call the recursive step. That's the part where you open the doll you're holding. In code, it's the part that basically says, okay, this problem's still too big, so I'm going to call myself to handle the smaller doll inside. But the second rule? This one's the biggie. It's the base case. This is that moment you get to the tiny, solid doll that just won't open. The job's done.
Seriously, you have to think of the base case as your escape hatch. It's the ultimate stop sign. It is absolutely 100% critical. Because without it, well, our program would never find that final doll. It would just keep trying to open smaller and smaller imaginary dolls forever until it completely runs out of memory and the whole thing crashes. All right, enough with the dolls for a second. Let's see how this plays out with a classic bit of math, the factorial. If we want to find the factorial of 5, written like this, 5 factorial, well, the definition is just 5 times whatever 4 factorial is. See what we did there? We just defined the problem in terms of a smaller version of itself.
So what's 4 factorial? Well, same logic, right? It's just 4 times 3 factorial. You can see the pattern starting to emerge. We're just peeling back one layer at a time, using the exact same logic on a smaller and smaller number.
And we just keep going. 3 factorial becomes 3 times 2 factorial. And all these earlier problems, the 5 times, the 4 times, they're all just kind of put on hold, waiting in line for these smaller problems to get solved first.
And we keep going until, bam, we hit 1 factorial. And we know the answer to that. It's just 1. That's our base case. The recursion stops, and now that answer, that 1, gets passed back to the function that was waiting for it. So 2 times 1 is 2, and that result gets passed back up the chain, which solves the next piece, and so on, until the very first problem gets its final answer, 120. It's like a chain reaction in reverse.
So right about now, you're probably thinking, hang on, couldn't I have just done that with a simple loop? And yeah, you're totally right. You absolutely could. Which brings us to a really important comparison. Recursion versus its good old workhorse cousin, the loop. This really gets to the heart of the trade-off. Recursion can be just incredibly clean and elegant, especially for problems that naturally break down into smaller pieces, like searching through a file system. But there's a price. Every single time a function calls itself, it has to remember where it left off. All that I'm waiting for an answer memory gets piled onto something called the call stack. Loops might feel a bit clunkier sometimes, but they don't have that memory problem.
And, it turns out recursion isn't just one thing. It has a few different flavors, different styles, all based on how that recursive call is made. So let's take a quick little tour.
First, you've got tail recursion. This is when that call to itself is the absolute last thing a function does. There's no math or anything left to do afterwards. Because of this, it's often called a glorified loop. And a lot of modern systems can optimize it so it doesn't even use that extra memory. Then you have indirect recursion, which is kind of like a game of tag. Function A calls function B, which might call function C, which then calls function A again. The circle is complete. But then, things get really weird with nested recursion. This is where a function doesn't just call itself, it uses a call to itself as one of its own ingredients. Go back to the nesting dolls. Imagine that to figure out what doll is inside, you first have to go open a completely different set of dolls and get the answer from that. Yeah,
This is where the complexity can just explode. And that powerful, sometimes explosive nature, that brings us to the dark side of recursion. Because for all of its elegance, when it goes wrong, it can go very, very wrong. The most common mistake, the classic blunder, is messing up your base case. If the recursion never gets its stop signal, it just keeps calling itself, adding another layer and another onto that memory stack. Imagine stacking plates. Eventually, the tower gets too high, becomes unstable, and the whole thing comes crashing down. That's your Stack Overflow error. But it's not just about crashing. Sometimes a recursive solution is just shockingly slow. The textbook recursive example for Fibonacci numbers is a perfect case. To figure out the fifth Fibonacci number, it has to calculate the fourth and the third. But to get the fourth, it has to calculate the third all over again. This wasteful recalculation just cascades down, forcing the computer to do the same exact work over and over and over.
And if you want to see just how truly insane this can get, you have to look at the Ackermann function. It's a type of nested recursion, and it grows so unbelievably fast that with simple inputs, like just 4 and 2, the result is a number with so many digits that it's larger than the estimated number of atoms in the entire known universe. It's not just slow, it's literally impossible to compute. And that really brings us to the final question, doesn't it? Recursion gives us this powerful, often beautiful way to approach problems. It can shrink complex logic down to just a few lines of code, but it comes with very real dangers: memory crashes, brutal inefficiency, and complexity that can literally break your brain. So I'll leave you with this. When you're staring down a problem, how do you decide if that elegance is really worth the risk?